All right, welcome to Learning Activity 10. We're going to continue to look at convolutional neural networks. And in this unit, we're going to look at this Caltech image database. It's a common image database. It's got this version has 256 different categories, and it has a bunch of images in each category, and they're pretty diverse sets of categories. So that's what we're using today, and they're pretty large images for them. So in total, there's about 30,000 images, and again, 256, 257 categories here. And the images, they're not huge, but they're range from like 150 by 150 pixels to about 600 by 600 pixels. So in that range. So they're not giant images, but they're certainly a good size for us to work with for this. So, and again, this module is broken up into three main sections, section 1, 2, 3. But in order to get any of those sections to run, you have to run section 0, and there's quite a bit of code in section 0 to get everything set up here. So let's start by running the code in section 0. I've actually run all this code. So again, first code here, we're going to import our libraries. Here's some samples of the images we're going to look at. So there's like a category is just called dice, and a whole bunch of images of different kinds of dice. Another category is just called ducks, and another category is just called dogs. Now there are 257 different categories here, but we're just going to choose 20 of those categories. And as you can tell by the dice, ducks, and dogs, the categories I chose were like the D's and E's of the categories. So we're just doing, there'll be 20 different categories we're going to put images into here. This command will get the data from a spot I've chosen. So this data set is actually quite large, and if you were to download this is 1.2 gigabytes and quite big. And so I've cut that way back, and so this, otherwise it would take about an hour to maybe download that and set it up here, and I didn't want to do that. So we have a limited set. So this should just take a couple minutes to load, and it will load in here. There'll be a folder for our data in here, and then the Caltech images will be over here. And again, we just have 20 different categories, and it's broken up into training and testing data. And so yeah, everything from covered wagons to diamond rings, dolphins, Eiffel Tower, eyeglasses are what we're working with here. And then in each of these categories, there'll be a bunch of images here. So this is all images of crabs for us to look at. So. All right, so and again, you don't necessarily have to look at those images, but just so you know that that's where they're showing up here. My cat's just joined me on my lap. Sorry about the little noise here, but okay. So this brings in and imports the images here. Now this displays some of the samples. So here's a bunch of the dog pictures. Here's a bunch of the fern pictures, just to give you an idea. These are small, again, versions of the larger pictures out there. We set up these callbacks as we've done before for early stopping and to reduce the learning rate as we go. We also have to set up some image handling here. So here's where we're setting up the folders where we're reading the images from. We have one, what we call a validation folder, and a training folder. So the training folder are the images we'll use for training, and the validation folder or test folder, those are only used for validating or testing the model, and there's no training done. So the model only sees those during the validation stage. We create what are called image generators here that are going to scale these images here, and then we also have this special method called flow from directory. So this is a Keras method that will randomly pick images from the different directories, randomly select different categories so that all the categories are covered, and randomly select images from each of the folders from the categories and display them. It will resize the images so that all the images are the same size, and do some other small things. Like I said, we rescale the pixels, so each pixel is a value between 0 and 1 here. Now the image size we set up is 224 by 224. That just works with a number of these models we're going to work on. You can actually use different sizes here, but I think this should work for most of our models. So that's the image size we're going to be working with. Okay, so once we've done all of that, then we're going to look at three different types of CNNs. The first one is a CNN you define and train, so kind of a custom CNN. That's what we've been doing in the last unit. Then we're going to look at pre-made models, much more sophisticated models that are already pre-trained, and then we're going to look at those pre-trained models and do some more different training on them. So first you'd go through section 1 here, and again this kind of reviews the different models here, and this is our kind of a basic model I have set up here for this, and it's probably easier if I just show you the results here from this model. So we start with images that are 224 by 224, and we do a 2D convolution on it here, and another one, and then we do max pooling, and that cuts the image size down to 110 by 110. So that's first layer is up here, 2D convolution with 8 filters, another 2D convolution with 8 filters, and then a max pooling layer. So then we do this convolution with 16 filters and another max pooling layer, and a convolution with 32 filters and another max pooling filter, and you can kind of see that here. So we were at 110 by 110, we did another convolution layer, and now we're up to 16 filters, and we did max filtering, that max pooling, that cuts the image size in half. We're down to 54 pixels, but we're up to 16 filters, and then we do another convolution. So now we're up to 32 filters, another max pooling, and that cuts the images down to 26 pixels, and then another convolution, so we're down to 24, and then our final max pooling cuts the image size down to 16 by 16 with 64 filters here. So that's this final filter and max pooling. Then we flatten the images, we do a dense unit, and then we do an output unit here. So that's what we have, and so we ended up with 2 million parameters here, which is quite a few parameters. So basically these are 2 million trainable weights, connections between the different neurons in our model here. Then we're going to train this here, going to run this. Above we actually set something called the batch size here to 8, and what that means is that rather than doing one image at a time, we'll do 8 images at a time for each one. And so here we do 100 epochs, and each epoch, 100 steps per epoch, and each step will be one batch. So that'll actually do 800 images here to go through this, and then we'll do this for 50 epochs, 50 training times. So this will just run through the training. Now, because of we're implementing this early stopping. If the training doesn't improve, it should stop automatically. So often it won't run for 50 epochs. Here this one ran for, well, I guess 44 epochs. Oh no, that was learning rate reduction, and then we stopped for the results here. So this is the accuracy I finally got here. So my final accuracy was 99%, which was really good, but that's on the training data. It was only 81, maybe 82% on the testing, on the validation accuracy. So here's kind of a plot, and you can see again with our accuracy, the training went up pretty high, but the validation stuff did not go. And often when I see this, I think maybe we should have some dropout layers or something like that in here. Okay, so then for your write-up here, I want you to describe the database we're using. Describe what I want you to do is do some changes to this base data set, the base convolutional model. Add some more layers, maybe add more filters, different filters, try out some dropout layers. There's a special kind of dropout layer that you can use in convolutional data networks called a spatial dropout 2D layer, so you could try that. But again, just try, and again, it's kind of random. You don't know a lot about this, but just try out some different things and see if you can improve upon it. So just do one different configuration and do it. And what we're going to do is have everyone share their trials. So in the discussion area, I want you to create a post under this Learning 1 Custom CNN Results. You're going to do a couple of these, but this is for section 1. And say how many layers did you use, how many trainable parameters, how long did it take, and the accuracy. And again, you can find that all up here in the model. So when you compile the model, it'll tell you how many total parameters and how many trainable parameters, and in these examples they'll both be the same. When you train your model, it'll generally tell you how long each epoch takes, and this is actually running relatively quick here. And then the final accuracy will be displayed, the training accuracy and the testing or validation accuracy here. So 99% and 80, I'm rounding up to 82% here for that. Okay, so that'll be your write-up for the first part. Now for the second section, we're going to use these pre-trained models. And there's a couple articles I want you to read. One of these articles on pre-trained models, and they will go over some of the common architectures. Like one of the first architectures out there was called VGGNet, and original one was VGG16. And it isn't that much different than what we have. It starts with the input image, and then we do 3x3 convolutional filters. We do 64 of them. Another 3x3 convolution with 64, and a max pooling layer. 3x3 with 128. So now we are getting more filters, and another 3x3 with 128 filters pooling. 3x3 with 256, 3x3 with 256 filters pooling. Some more of this. Now we're using 512 filters in each of these layers pooling, and another 512 with pooling, and then some dense, what are called in their terminology it was called fully connected layers, but in our terminology they're called dense layers. So some dense layers with 4,000 images here, or versions here. So that's one of these common ones. VGD19 is just a little larger version of that. But again, there are some more complicated ones. So this is called ResNet, which uses convolutional neural networks and some special connections between them. So not only do they have a set of convolutional layers, but they have some connections in between these convolutional neural networks, and talk a little bit about that. Inception was originally developed by Google and had these very complicated modules. So each of these modules, you'd have the input, and it would go into the whole set of these different filters, a bunch of 1x1s and pooling filters, and some 3x3 filters, and a 5x5 filter, and then all these filters were then concatenated together, and this was called an inception model. And then these inception models were tied together in this system. So there are different networks like this. I want you to read up a little bit about how some of these work, because Keras has a bunch of these built in to our system. So if I look at the instructions here, they have all these models built in. So they have the VGG16, they have the Inception, a couple versions of the Inception model built in. They have what's called DenseNet, on ResNet, and Exceptions. They have these models all built into our system. So here's our neural network system. So now we can just use one of these neural network systems. So let's say we wanted to use VGG. That's this one. I'm going to uncomment that one and comment this one. So this is, oops, did that wrong. Try that again. All right. So the one line that doesn't have a pound sign is the one line that's not commented out that we'll use. And in this case, it's the VGG. So this will create a VGG model, define all the things. It's going to load it in with pre-trained weights with a data set called ImageNet, and you'll learn more about that in the questions. We're going to do what's called not include the top. So again, if I go back here to VGG, the top is this dense networks at the top and this final softmax. So we're always going to exclude this top couple layers from our network, because we are then going to add our own top on. So we're always, and all these will include the top. And the input shape is always going to be set because all of our images are resized to 224 by 224, and 3 because their color images RGB, red, green, blue. Okay, and then right now we're not going to train this, so we're going to load in this pre-trained model, and we're not going to let any of these weights be changed. And in the next model we'll change this, but for now we're going to do this. So now we define this as our pre-trained model, and in our actual model we're using, we're going to build it from our pre-trained model, and then we're going to add the top layers, and our top layers are just going to be instead of a dense layer or a flattening layer, we're going to use this global average pooling, which is a little easier to manage because we'll have different size inputs from these different layers. So we'll do a global average pooling layer here, and then we'll do our final dense layer with our 20 outputs here. And then we'll just print out our summary. So now we'll run this here, and you'll get the results. So this is actually the results from the previous one. It has lots. Look at all these blocks. This network is just huge here, and has 2 million parameters in this version. But let's do VGG. That's what one we did. So I'm going to run this here. And again, this is VGG. The model is VGG, and it'll show the layout of VGG here. And it only has, well, it has 14 million connections here. So it also has a lot. And you'll see two things. You'll see the printout of the original VGG model, and then our special sequential model is set up. So it'll show us that there's a lot of weights that are not trainable. So this is the total weights or parameters, and only 10,000 are trainable, because again, we're only training the top part of this network. We are basically taking this architecture here, all these layers is going to be pre-trained, and we're just going to cut right here and put in our own little top one layer and then a softmax at the end, and only train that part and leave all this stuff fixed here. So then when you train this, hopefully training will go relatively fast through this. Even though this is a huge model with lots of connections, there's 14 million parameters or weights in here. Training will still go relatively quickly, 6 seconds, 5 or 6 seconds per set here as we go through this. And then you can look at your results and display them. So for your write-up, I want you to look a little bit at this ImageNet data set that we'll be looking at, describe that. I want you to select one of these models and do a little research on one of these models. So pick one of these models, Google it, or somehow do some research, find one article, at least one article about it, and research that and do that. So you want to post a summary of that with a citation to your article you found. And then what is your performance? How did your results show up here? And then I want you to post that also to the discussion area. So I'll have a separate discussion. Now the first one was called custom one. I think I'll add section 1 to that. And then the next one will be called pre-trained models for section 2. And post your results so we can all see, because everyone will pick one different model. It'll be interesting to see how the different models perform. I haven't even run all the models on this data set. So now the final thing I want you to do is section 3 is similar to this, not that much different. Again, you're going to use the same pre-trained models, but the one thing we're going to change is that the pre-trained models trainable, we're going to set this to true. And what that will do is originally we said we took this model that's been pre-trained on this set of images, and we didn't change any of these weights. Those are fixed, and the only weights we changed were on the top part of the model. Now we're going to change this so that our training can change all of these weights. So they'll all be trained initially except for the top, but they can be tweaked so we can tweak them, and sometimes this is called fine-tune training. So we've got the basics set up, but we can fine-tune them to our data set and our needs. Again, pick your model, again the same one you did before up here. So again, like I did VGG before, so I would want to do that again here. Make sure you leave this as true here, and we set up the network the same way here. And one thing you'll find is that when you run this, training will be a lot slower here, because it's training a lot more weights. So in this example, there'll be let's just do this. This version had 2 million total weights, and almost all of them are trainable for this. And VGG will be even more than that. So. Okay, so then you train this, and then again you'll report your results, and post those to the discussion area. Now, one other thing one of the problems we run into when working with these data sets are bias. Especially bias may have been in our original data set, and then we'll use that pre-trained data set to create other data models, and often companies will reuse or buy models from other companies and reuse these pre-trained data sets out there, and they might have bias in them. And so that's happened in facial recognition systems based on pre-trained models. And so I want you to watch, I really am a fan of Joy here, and so she's got a couple great videos. I think this is a good one. It's talking about bias and how she's a grad student at MIT and has worked a lot at MIT on fighting bias in algorithms and machine learning. So I'd like you to watch this video and then post a reaction to this, and especially try to tie in a little your knowledge now of how CNNs work and how these systems actually use pre-trained data in their models. So this is your final post. Now, if you want to learn some more about this whole topic is often called transfer learning, and so here's a guide if you want to read more about transfer learning. You can look at that. Hope you enjoy this unit.